When is a liquid a liquid? We've already looked at solids. Solids are going to take on this very structured formula. Think of an ionic compound, an Na to a Cl, which goes to an Na, just like this. So we get this very rigid structure. So it has a set volume, right? This isn't going to shift around. It's not going to expand outward or shrink down. This is a set volume. It is also a set space. It's got its own shape. This is like this drawing that I made is the shape of a square. When we go to a liquid, that's all going to change. Suddenly, like in an ionic compound, if I've got a liquid here, let's just make it a bowl, it's going to take the shape of that bowl, and I'm going to have sodium and chlorine bits just floating around, just moving around each other. They're still attracted to each other. They're still, those forces are strong enough that it keeps them close together, but they're not going to be in this same rigid structure. If I took this same stuff and I poured it into a beaker, well then it would take the shape of that beaker. So I'd have Na and Cl just moving around here, just wherever they can go, wherever they can fit in between each other, just kind of sliding around each other. If I poured that out onto a tabletop, which I wouldn't recommend because sodium chloride is extremely hot when it's molten, then there's a tabletop. Well, then it's just going to form a puddle with no definite shape. And it's going to still have those NAs, those CLs just floating around each other. If it was in space, it would form a perfect circle. It would just hold itself together in a perfect circle. Okay. So that's what our real big difference is. Once we go to a liquid state, we still have a definite volume. Liquids are generally not compressible. Not like air, where if you take a balloon, you could squeeze it down and shrink it. Liquids are already as compressed as they can be. You can't squeeze it into a smaller shape. So they have a set volume, but they do not have a set shape. So let's get started. When you melt an ionic substance, what type of bond do you break? You break an ionic bond. Okay? When you melt a network covalent bond, what type of bond do you break? You break a covalent bond. And different bonds have different strengths, so these two can overlap in their strengths. When you melt a molecular solid, what type of bond do you break? Well, there's going to be three options. You're either breaking a polar bond, a hydrogen bond, or an a London dispersion force. I work with so many acronyms, it's hard to keep them all straight. Okay, so this example right down here, HCl, this is going to be a hydrogen bond between these two, right there. That would be a hydrogen bond between these two guys. So label the type of force above, intermolecular or intramolecular. Remember, intermolecular is between two molecules. Intramolecular is within a molecule. Intra. Okay. What is the difference between an intermolecular force and an intramolecular force? Well, the intermolecular force keeps stuff together, keeps separate molecules together, can determine physical properties. Okay, and I'm running out of room here, so I'm just going to say this next part. So intermolecular forces, it's what holds these individual molecules together, and it can determine physical properties. Certain physical properties like melting point and boiling point. But the intramolecular forces, this is really going to determine the chemical properties. Chemical properties. So the chemical properties are things like reactivity or taste or smell. Although I don't recommend tasting a lot of things like hydrogen chloride. It's an acid. It'll hurt very badly. Taste, smell. So there's actually a video I found on YouTube of a bunch of Australians trying out different chloride salts. So there's NaCl, there's LiCl, there's all these different chloride salts based on that first row of the periodic table, right? Okay. There's all those different salts based on the guys in this first row right here. And they tried all of them to see which ones taste the best. Are there better ones than sodium chloride? What they found is that sodium chloride tasted the best. Lithium chloride tasted similar. It tasted like a weak salt with a little hint of lemon. So that was interesting. And everything else just tasted like pure farts. So that is an example of chemical properties. That's determined by the intramolecular forces. Okay. Student hypothesis. A substance is a solid at room temperature because molecules stick together. The reason they stick together is that they really like each other. Justify or nullify. Obviously, this is a ridiculous hypothesis. But why? It's not because they really like each other. What makes them want to be around each other? What causes them to stick together? Well, there's got to be some force, intermolecular, likely, intermolecular. The only exception would be a network covalent bond. Remember, that's the only time that we have an intramolecular force keeping everything together, because we really count an ionic bond as being both inter and intramolecular. So some force, it would be likely an intermolecular force, keeps them together. Keeps molecules together. So nullify, definitely not. Right, what is the only reason two molecules would stick together? Well, what is it? Well, there's got to be some force keeping them together. Molecules aren't just going to sit near each other naturally, right? It's not like I've got these two markers. They'll sit here as long as there. Now they're just going to sit there. They're not moving, they're just sitting there near each other. The problem with that idea is that molecules are in constant motion. They have all this energy. They're not just going to stop moving. Even in solid phase, they're going to keep moving around. And so if there's nothing keeping them coming back to each other, they're naturally just going to drift apart. So if molecules are sticking together in a solid or liquid, then some force has to be acting on them to keep them together. We know that that has to occur. All right, what is needed for a hydrogen bond to occur? Well, that is the NH, FH, or OH bonds. It's got to have one of those three options because these are so polar that they are a step above every other polar bond. This up here, this would be a polar bond, and a hydrogen to oxygen or fluorine or nitrogen would be, if I remember correctly, about 10 times greater than this bond itself. All right, what is needed for London dispersion forces to occur? Well, really just an electron cloud. The more cloud, the more force. We can see this in something like iodine. Iodine is a very large molecule. It has a very large radius. Iodine has a huge electron cloud. Compare this with fluorine, which has a tiny electron cloud. Iodine has it's so many more times the size of fluorine that this massive electron cloud causes two iodine molecules when they overlap in molecular iodine, that it is a solid at room temperature. Remember, iodine is one of the halogens. You can look that up in a periodic table. F2, just a few rows above iodine in the same column of the periodic table, is a gas at room temperature. So is chlorine. However, bromine, one above iodine, bromine 2, Br2, this is a liquid at room temperature. It has a smaller electron cloud. Now compare this with things like oils, things like alcohols that have hydrogen bonding going on. Well, I guess that's not a good example. But things like fats and oils, these would be liquids. A lot of oils are liquids at room temperature, and they have a massive number of carbon to hydrogen bonds. They have these very long bonds. They're very long. And so because they've got all of this extra electron cloud, they want to stay close to each other. These London dispersion forces get a lot bigger. So London dispersion forces are really going to be based on how much electron cloud is there. All right? Okay, indicate the type of force that is causing the substance to be a solid, liquid, or gas. Order them from highest to lowest melting points. Okay, so we're going to do this again. We did this once before. Let me just get some room here, and I'm going to zoom in real quick. Okay, MgCl2, well, that's going to be ionic. That's going to be the driving force here. H2, that is going to be London dispersion forces. Remember, the H2, there's no way for it to be polar, H to H. There's no electronegative difference there. This is going to be covalent. Diamond is a bunch of carbons all strung together, so it's covalent network solid. H2O, that's going to be hydrogen bonding. Let's just say HB for hydrogen bonding. NaCl, that's going to be ionic. C5H12, that is again going to be London dispersion forces. But the difference here is C5H12, there are a lot more electron cloud. There is a lot more electron cloud there to keep it together than an H2. So let's order this. From highest to lowest melting point. So starting at the highest melting point, well, diamond has one of the highest possible melting points, so we know that's up here, carbon. That's going to be the highest melting point. If we weren't sure about diamond, if it was some other covalent network solid, like quartz or something, we might need to look up the melting point compared to the highest melting point ionic solid. But this one, diamond, definitely going to beat it out. Something like 5,500 degrees Celsius. It's a ridiculous number. The next one is going to be MgCl2. We're going to go from our covalent network solids to our ionic solids. So ionic MgCl2 is going to have a larger charge. It's a +2 charge, remember, versus Na, which has a +1 charge. So a bigger charge, higher melting point. Okay, then we're going to go to NaCl. All right, so that's our ionics. Next we have our LDFs and our hydrogen bonding. Well, hydrogen bonding is always going to beat out those London dispersion forces. Well, almost always. There's very few cases where it doesn't. So hydrogen bonding next. Oh, I should list the molecule, H2O. And then we're going to have our London dispersion forces. Now, like I already established, C5H12, that's going to be C1, 2, 3, 4, 5. That's going to have a lot more of an electron cloud to work with. So it's more easily going to stack up and stick together. Remember, these are hydrocarbons that we played around with at the very beginning of the year. So C5H12, that's going to have a higher melting point. And then our last one, H2, hydrogen gas. Obviously, that's a gas at room temperature. We already know that. Fantastic.